Let's talk about Green's theorem. Some books will call this thing Green's theorem in the plane because it only happens, well, in a plane. Well, okay, before introducing the theorem, let capital C be a closed curve. Just recall that the word closed here just means that the curve should start at the same place that it ends. So among closed curves, there's really more or less two kinds. So I'm going to try to draw the same curve twice. Actually, why don't I just copy paste this curve here? I'm going to copy, paste. So, okay, there's the same curve twice, but you might orient it this way. We'll just put in a couple times what the orientation looks like, or you might orient it the other way. Now, this is the right one, sort of. I mean, this is nice because this one's the counterclockwise orientation. And think about the unit circle, how we orient that counterclockwise. So this is the counterclockwise or the positive orientation. It's the default that we like anyway. And then this is the clockwise or the negative orientation. Alright, so then let's introduce what Green's theorem itself is. So Green's theorem, or Green's theorem in the plane, is stated this way. So let capital C be a closed counterclockwise, or positive orientation, curve bounding a region capital D in the plane. Then the integral, the line integral over C of P dx plus Q dy is equal to the double integral over the region D of partial derivative of Q with respect to x minus partial derivative of P with respect to y dA. Okay, so there's the theorem itself, but we're going to make some comments about it, so I haven't fully closed off this box yet. So this part right there, we'd just like to comment that we've seen this in different forms. So this is actually, just as a reminder of some old things, this is equal to, this is equal to the integral over the curve C of f dot dr, where f is the vector field where the first component is p and the second component is q. Now, some other comments about this is that sometimes this is written. Okay, so sometimes this is written. This is written integral sign and still over a C, but then funky thing happens is that inside the, or somewhere in the, just in the middle of the integral sign, let me try this better, it's the first time around, there's just a circle drawn as part of the integral symbol. P dx plus Q dy. Sometimes other books prefer actually to include inside this picture a little something that shows that counterclockwise orientation by drawing part of a little arrow. So let me try that, draw that a little smaller so that, okay, something like that, okay? P dx plus Q dy. Now, let's say a little something about the terminology and the notation. There's a lot to get used to here. So, for Green's theorem, we'll say language like C bounds D. We'll also use language like D is the boundary of C. So there's notation. There's a notation way of saying D is the boundary of C. So D equals, and I know it looks like the partial derivative symbol because that's the same symbol, C. And so this, when you see this symbol written in front of a set, So capital C is a set, right? It's a geometrically, it's some shape. It's a curve. When you see the symbol in front, this means boundary of. Okay, let's draw a picture of what is being meant by all this kind of stuff here. So, as just a general picture of what's going on, so you're in the plane, and there's this closed curve. Maybe, let's not make it so uniform. How about like this? There, closed curve. Oriented counterclockwise. Maybe we'll draw one more orientation arrow here. So you zip around this thing, traveling along this way. So you're moving counterclockwise, say along the racetrack. So that's the curve C. The curve C bounds a region inside. So we'll shade this region inside, this two-dimensional region. It's like the part of the racetrack that you shouldn't be in because you're trapped in there if you go there. And so that is capital D here. Okay? So C and D are both drawn in the plane, but C itself is a curve. It's really a one-dimensional creature in nature, right? It's the string around the outside, while D is the shaded in portion in between. And so all of this, I hope, makes sense that, let me use the same colors here. C, here, this is a line integral on one side, right? There's a line integral. And Green's theorem is telling us that what you get is the same as if you just computed a double integral over a two-dimensional region, right? So this integral over D here, it's over a filled-in two-dimensional region. We will, of course, be looking at many examples. Tune into the next part.